let's say we have some function f, and it's a mapping from the set x to y. So if I were to draw the set x right there, that's my set x. And then if I were to draw the set y just like that, we know, and I've done this several videos ago, that a function just associates any member of our set x. So I have some member of my set x there. If I apply the function to it, or if we're dealing with vectors, we could imagine instead of using the word function, we would use the word transformation, but it's the same thing. We would associate with this element, or this member of x, a member of y. So that's why we call it a mapping. It says, hey, that guy, when I apply this function, let me do it in a different color, this little member right there is associated, this little member of x is associated with this member of y. And you would, if this is right here, this is a capital X. So let's say we call, well, let's say we call this a, and let's call that b. And we would say that the function where a is a member of x and b is a member of y, we would say that f of a is equal to b. This is all a review of everything that we've learned already about functions. Now I'm going to define a couple of interesting functions. The first one, and I guess it's really just one function. I said it's a couple, but I'll call it the identity function. Identity. The identity function. And this is a function, I'll just call it a big capital I. And its identity function operates on some set. So let's say this is the identity function on set x. And it's a mapping from x to x. And what's interesting about the identity function is that if you give it some a that is a member of x, so let's say you give it that a, the identity function applied to that member of x, so the identity function of a, is going to be equal to a. So it literally just maps things back to itself. So the identity function, if I were to draw it on this diagram right here, would look like this. It would look like, let me pick a nice suitable color. It would look like this. It would just kind of be a circle. It just points back at the point that you started off with. It associates all points with themselves. That's the identity function on x. Especially as pointed as it applies to the point a. If you applied it to some other point in x, it would just refer back to itself. Now that's the identity function on x. You could also have an identity function on y. So let's say that b is a member of y. So I drew b right there. Then the y identity function, so this would be the identity function on y, applied to b, would just refer back to itself. It would just refer back to itself. And so that would be equal to b. This is the identity function on y. And so you might say, hey, Sal, these are kind of silly functions, but we'll use them. They're actually at least a useful notation to use as we kind of progress through our explorations of linear algebra. But I'm going to make a new definition. I'm going to say that a function, let me pick a nice color, pink. I'm going to say that a function, or let me say f, since we already established it right over here. I'm going to say that f is invertible. Invertible. Introducing some new terminology. F is invertible if and only if the following is true. So if and only if the following is true. I could either write it with this two-way arrows like that, or I could write it as if with two f's. That means that if this is true, then this is true, and only if this is true. So this implies that, and that implies this. So f is invertible. I'm kind of making a definition right here. If and only if there exists a function, we'll call it, I'll call it nothing just yet. I'll call it something in a second. And I'll write it as this f with this -1 superscript on it. So f is invertible if and only if there exists a function f inverse, well, I guess I just called it something, f inverse, such that, let me do that in purple, such that if I apply f, remember f is just a mapping from x to y. So, and let me read it. So this function f inverse is going to be a mapping from y to x. So I'm saying that f is invertible if there exists a function, f inverse, that's a mapping from y to x, such that if I take the composition of f inverse with f, this is equal to the identity function over x. So let's think about what's happening. And this is just part of it, actually. Let me just complete the whole definition. This is true, this has to be true, and f, the composition of f with the identity function has to be, the composition of f with the inverse function has to be equal to the identity function over y. So let's think about what's this saying. There's some function, f, we'll just call it, well, I'll call it right now. This is called the inverse of f. This is the inverse of f. And it's a mapping from y to x. So f was a mapping from, let me draw it up here. So f is a mapping from x to y. We showed that. This is the mapping of f right there. It goes in that direction. We're saying there has to be some other function, f inverse, that's a mapping from y to x. So let's write it here. So f inverse is a mapping from y to x. So f inverse, if you give me some value in set y, I go to set x. So this guy's domain is this guy's codomain, and this guy's codomain is this guy's domain. Fair enough. But let's see what it's saying. It's saying that the composition of f inverse with f has to be equal to the identity matrix. So essentially it's saying if I apply f to some value in x, right? If you think about what's this composition doing? This guy is going from x to y, and then this guy goes from y to x, right? So let's think about what's happening here. F is going from x to y, and then f inverse is going from y to x. So this composition is going to be a mapping from x to x, which the identity matrix or the identity function needs to do. It needs to go from x to x, and they're saying this equals the identity function. So that means when you apply f on some value in our domain, so you go here, and then you apply f inverse to that point over there, you go back to this original point. So another way of saying this right here is that f, let me do it in another color, that f inverse, the composition of f inverse with f of some member of x, of the set x, is equal to the identity function applied on that item. This is what these two statements are equivalent. And so by definition, this thing is going to be your original thing. Or another way of writing this is that f inverse applied to f of a is going to be equal to a. That's what this first statement tells us. And if you think of it visually, it's saying you start with an a, you apply f to it, and you get this value right here. That is f of a. I'm saying it equals b, or I said it equaled b earlier on. But then if you apply this f inverse, and it doesn't always exist, but if you apply that f inverse to this function, it needs to go back to this. By definition, it needs to go back to original a. It has to be equivalent to just doing this little closed loop right here when I introduce you to the identity function. Now that's what this statement is telling us right here. The second statement is saying, look, if I apply f to f inverse, I'm getting the identity function on y. So if I start at some point in y right there, and I apply f inverse first, if I apply f inverse, maybe I go right here. Maybe this point, let's call that lowercase y. So this would be f inverse of lowercase y. And then if I were to apply f to that, I know this chart is getting very confusing. If I apply f to this right here, I need to go right back to my original y. So this, when I apply f to f inverse of y, this has to be equivalent of just doing the identity function on y. So that's what the second statement is saying. Or another way to write it is that f of f inverse of, let's say, of y, where y is a member of the set capital Y, it has to be equal to y. And you've been exposed to the idea of an inverse before. We're just doing it a little bit more precisely because we're going to start dealing with these notions with transformations and matrices in the very near future. So it's good to be exposed to it in this kind of more precise form. Now, the first thing you might ask is, hey, let's say that I have a function f. Let's say I have a function f, and there does exist a function f inverse that satisfies these two requirements. So f is invertible. F is invertible. The obvious question, or maybe it's not an obvious question, is f inverse unique? And actually, probably the obvious question is, how do you know when something's invertible? And we're going to talk a lot about that in the very near future. But let's say we know that f is invertible. How do we know, or do we know, whether f inverse is unique? And to answer that question, let's assume it's not unique. So if it's not unique, let's say that there's two functions that satisfy our two constraints that can act as inverse functions of f. So let's say that g is one of them. So let's say g is a mapping. Remember, f is a mapping from x to y. Let's say that g is a mapping from y to x, such that if I apply f to something, and then apply g to it, so this gets me from x to y, and then when I do the composition with g, that gets me back into x. This is equivalent to the identity function. This was part of the definition of what it means to be an inverse. So I'm saying that g is an inverse of, I'm assuming that g is an inverse of f. This assumption implies these two things. That assumption applies those two things. Now let's say that h is another inverse. Let's say that h is another inverse of f. H is another inverse. By definition, by what I just called an inverse, h has to satisfy two requirements. It has to be a mapping from y to x. And then if I take the composition of h with f, I have to get the identity matrix on the set x. Now, that wasn't just part of the definition. It implies even more than that. If something is an inverse, it has to satisfy both of these. The composition of the inverse with the function has to become the identity matrix on x. And then the composition of the function with the inverse has to be the identity function on y. So let's write that. So g is an inverse of f. It implies this. And it also implies, I'll do it in yellow, that the composition of f with g is equal to the identity matrix. Sorry, I keep saying matrix. The identity function on y. And if we do it with h, the fact that h is an inverse of f implies that the composition of f with h is equal to the identity function on y as well. And just as a reminder, let me redraw what I drew at the beginning, just so we know what we're doing. So if this is the set x right here, let me do it in different color. Let's say this right here is the set y. We know that f is a mapping from x to y. What we're seeing is, what we're trying to determine is f's inverse unique? So any inverse, so we're saying that g is a situation that if you take the composition of g with f, you get the identity matrix. So f does that. If you take g, you're going to go back to the same point. So it's equivalent. So taking the composition of g with f, that means doing f first, then g. This is equivalent of just taking the identity function in x. So just taking an x and going back to an x. It's equivalent to that. So this is g right here. And the same thing is true with h. H should also be, if I start with some element in x and go into y, and then apply h, like that, it should also be equivalent to the identity transformation. That's what this statement and this statement are saying. Now, this statement is saying that if I start with some entry in y here, and I apply g, which is the inverse of f, I'm going to go here. So g will take me there. And that when I apply f then to that, so then when I apply my f to that, I'm going to go back to that same element of y. And that's equivalent to just doing the identity function on y. So that's the same thing as the identity function of y. And I could do the same thing here with h. Just take a point here, apply h, then apply f back. I should just go back to that point. That's all of what this is saying. So let's go back to the question of whether g is unique. Can we have two different inverse functions, g and h? So let's start with g. Remember, g is just a mapping from y to x. So this is going to be equal to, this is the same thing as the composition of the identity function over x with g. To show you why that's the case, remember, g just goes from, all these diagrams get confused very quickly. So let's say this is x and this is y. Remember, g is a mapping from y to x. So g will take us there. Is a mapping from y to x. And I'm saying that this g is equivalent to the identity mapping or the identity function in composition with this, because all this is saying is you apply g and then you apply the identity mapping on x. So obviously you're going to get to the exact same mapping or the exact same point. So these are equivalent. But what is another way of writing the identity mapping on x? What's another way of writing that? Well, by definition, if h is another inverse of f, this is true. So I can replace this in this expression with a composition of h with f. So this is going to be equal to the composition of h with f and the composition of that with g. And you might want to put parentheses here. Actually, I'll do it very lightly. You might want to put parentheses there. But I showed you a couple of videos ago that the composition of functions or of transformations is associative. It doesn't matter if you put the parentheses there or if you put the parentheses there. Actually, I'll do that. I'll put the parentheses there at first just so you can understand that this is the same thing as that right there. But we know that composition is associative. So this is equal to the composition of h with the composition of f and g. Now, what is this equal to? The composition of f and g. Well, it's equal to, by definition, it's equal to the identity transformation over y. So this is equal to h composed with, or the composition of h with, the identity function over y, with this right here. Now, what is this going to be? Remember, h is a mapping from y to x. Let me redraw it. So that's my x, and that is my y. H takes some element in y and gives me some element in x. Now, if I take the composition of, if I take the composition of the identity in y, so that's essentially, I take some element, let me do it this way. I take some element in y, I apply the identity function, which essentially just gives me that element again, and then I apply h to that. That's the same thing as just applying h to the function to begin with. So, just going through this little exercise, we've shown, even though we've started off saying, hey, I have these two different inverses, we've just shown that g must be equal to h. So any function has a unique inverse. You can't set up two different inverses, and if you do, you'll find that they're always going to be equal to each other. So far, we know what an inverse is, and we don't know what causes someone to be able to have an inverse or not, but we know if they have an inverse, how to think about it, and we also know that that inverse is unique.